I'm going to show you one of the most beautiful and crazy spaces in mathematics, and this is an introduction to topology. The space I'm going to talk about is the comb space, and what it is it's this comb which I've drawn here in red. It's in the xy plane. It has a peak going up at every number on the x-axis that takes the form 1 over n for a positive integer n. So 1, you have a peak going up all the way to 1. Half, you have a peak going up all the way to 1. 1/3, you have a peak going up all the way to 1, and you get the idea. 1 over n, you have a peak going up all the way to 1, and as you can see, the peaks are going to get really, really dense. As you get closer and closer to the x coordinate being 0 on the y-axis, your peaks are going to get really dense. But one important point is we do not have a peak on the y-axis itself. Okay, we do not have a peak there. So here it's just black. I haven't drawn any red here. And this is a very interesting space because it is connected but not path connected. And I'm going to explain to you what that means in this video and give you a rigorous proof as an introduction to topology. It's so much fun, and we're going to just dive into the intuition first. So to start off with, this is not path connected. And what do I mean by that? It's not path connected because while it is true that any 2 points on the comb, like if you are on one peak, okay, imagine we're like dots. You are on one peak and I'm on another peak. We can always connect to each other because what we do is we go down to the base. So I can sort of track this down. I can show you as a marker. We go down to the base, then we stay along the x-axis, then we go up to the other point. So we can connect any 2 peaks together just by using the base. So it's kind of connected, path connected, except this one isolated point here, it's not really possible to connect it to anything. You can intuitively see that because if you sort of imagine the path, where would it go? You know, you have like these discrete kinds of tops of the peaks of the comb that approach this point. They're all points of the coordinate. The general coordinate is going to be 1 over n comma 1, but there's no way to continuously, as a continuous function, to jump from this point, which is 0 comma 1, to any point of the form 1 over n comma 1. So that has to be captured precisely, which you will do, but I will say that this is a connected space. And I'm going to explain what that means too, and that's so counterintuitive because we can't connect 0, 1 to anything else by a path, but the whole thing is still connected. So what do I mean by connected? Okay, so I'm going to define this very precisely and give you the intuition. So a connected space, so if we have a subset, so here's a definition. So let X be a subset of the plane. Okay, X is a subset of R2, something in the plane like the comb space, okay, that we just drew down. Now, we say that X is disconnected, okay, so connected will be the opposite of disconnected. But we say X is disconnected if there are disjoint open sets, okay, and I'll explain what open sets mean very shortly, okay. I'm just going to write it down. I'll briefly explain that. If there exist disjoint open subsets U and V of the plane, open subsets U, V contained in R2, such that the following is true. So property 1 is that X is contained in U union V. Okay, so U and V together cover X, and we're going to think of them as like islands that are disconnecting X. Okay, that's going to be the idea. So they cover X, and the second condition is that U intersection X is non-empty, and V intersection X is also non-empty. Okay, those are the two conditions. And what this all means basically is, as I said, it's like islands. So we say a set is open. Okay, so a set is open in the plane if it's like a blob. This is a prototypical open set in the plane. Okay, it's just the shaded region here where I don't include the boundary, hence the dashed line. And the point is that anything inside the set has a wiggle room. Okay, there is some sufficiently small distance. It doesn't matter what, some sufficiently small distance. It doesn't matter which direction we go, you'll still remain in the set as long as you go that distance. Okay, so as you can see that there is a lot of wiggle room around a point here. And as you approach the boundary, you'll have less wiggle room, but you still have some positive amount of wiggle room that you can stay within the blob. But on the boundary, you can't. So that's why the blob doesn't include the boundary, because on the boundary, if you wiggle in the wrong direction, you'll exit the blob. Okay, so the blob doesn't include the boundary. It's an open set. That's what it means to be open. And we say a set is disconnected. What this is saying basically is that there are 2 such blobs that separate our set into 2 pieces. So a prototypical example is if I had something like the following. I'm going to draw it here. If I imagine 2 chunks, so I'm going to draw a star like Jag, and I'm going to draw another line segment like this, okay? Like let's say a plus sign, doesn't matter. All right, so in this sort of situation, we can separate our X into 2 blobs. Again, they're open, so you don't include the boundary, but you can sort of separate them into these 2 pieces, and it's everything inside. It's a shaded region inside. and that's what is going to disconnect our X, okay? So we say X is connected if they don't exist such blobs, such islands that separate our X into two pieces. And this makes intuitive sense. You know, disconnected means there are two parts of X. So we say it's connected if you can't kind of clearly say what the two parts are. And by clearly say, you mean you separate them by these islands, okay? So that's like a topological definition of connectedness, but it's counterintuitive because though it seems intuitive, it actually allows our comb space to be connected, okay? Our deleted comb space to be connected. And why is that? Well, I'm going to explain that first, and then I'm going to give a proof for why it is still not path connected. Okay, and I'll define what path connected means, though intuitively you kind of know the idea. So let's talk about connectedness first. All right, so the key point for the comb space being connected is the following. It's very intuitive. It's that if we forget about 0, 1, it is connected. We believe that, okay? That's not something I'm going to explicitly prove here. It's something you can rigorously prove, but it's intuitively clear that that's connected just because it's path connected. You can connect any 2 points on the comb aside from 0, 1 to any other. But then the question is, if you add on the 0, 1, why does it still stay connected even though we can intuitively see it's not path connected? So for that, we're going to give a mathematical proof. So here's the proof. So let's assume for a contradiction it's disconnected. Okay, so here's the proof. So proof is let U and V be a separation of X. Okay, so let U and V be disjoint non-empty open subsets such that, let's call the comb space C. Okay, C for comb. So disjoint non-empty subsets of R2 such that U intersection C is non-empty, V intersection C is non-empty, and such that C is contained in U union V. Okay, that's what we are starting off with. That means it's disconnected, and we're going to get a contradiction. Okay, now here's the point. One of these U and V, we're going to have to target our point 0, 1 because we agree that without 0, 1 it's connected. So we're going to have to target our 0, 1. So one of our open sets is going to contain 0, 1 by this condition that C is contained in U union V. So let's say without loss of generality that U contains 0, 1. Okay, so let's say that, so this is without loss of generality, W log, without loss of generality, it's an abbreviation, that 0, 1 is contained inside U. Okay, now here's the thing. Any open set in the plane that contains our 0, 1 is going to contain a whole lot of other points on the comb space. Why is that? Well, it doesn't matter if it's open. As I said, there's a wiggle room. So you can find some small wiggle room around the 0, 1 that has to lie inside U because U is open and 0, 1 is in U. But then this small disk-like region is going to contain pickets of the comb, parts of picks of the comb. It's going to contain parts of these vertical line segments because eventually, as you get closer and closer, you're going to start touching, the top end of it is going to enter into this disk. So therefore it has to be inside U because we don't know U, but we know it has this wiggle room around 0, 1. So that means that if we take the deleted comb space, deleted 0, 1, okay, so instead of just taking C, which is a deleted comb space, we take C prime, which is C minus 0, 1, just the point 0, 1. We've agreed that is connected, okay, that's the intuitive statement that is connected. But now we know that U intersection C prime is also non-empty. Okay, U intersection C prime is non-empty. We also, of course, know that V intersection C prime is non-empty too, because V intersection C is non-empty, and V did not contain 0, 1. So that means whatever points in C it contained were outside of 0, 1, and also therefore in C prime. So therefore V intersection C prime is non-empty. And U and V are again open, they're disjoint. So every condition is satisfied, and their union is going to contain C prime as well, right? But that is a contradiction because we know that C prime is connected once you delete 0, 1. That was the intuitive statement. So notice what we did here. We basically said that connectedness is kind of a bit more fuzzier than path connectedness. Basically, we couldn't separate it out into two discrete islands, even though it was not possible to connect 0, 1 to any other point. Okay, so that was our proof that using the fact that C prime is connected, that C is connected. And actually there's a general statement, if you know a bit more topology, the closure of a connected set is connected. Or if you add on limit points to a subset of the plane and that subset is connected, then that will still remain connected. So 0, 1 is a limit point of C prime because there are points of, what this means is there are points of C prime that limit to 0, 1. Okay, so adding on limit points doesn't destroy connectedness. So that's a bit of high level topology, but we're now going to get into path connectedness, and I love this proof. We're going to prove that C is not path connected. So we're going to have to define what that is, and I'm going to erase this part of the board before I do so. Let's define path connectedness. Even though we intuitively understand it, let's be very precise, like mathematically. So a subset of the plane, so again we say a subset X of the plane, like the comb space or whatever you like, is path connected if the following is satisfied. If for all xy in X, there exists a continuous function. So continuous function, this is going to be our path. So there exists a continuous function f from the interval. So there exists a continuous function f from the interval 0, 1 to x such that f of 0 is equal to x and f of 1 is equal to y. Okay, so in other words, there's a continuous function. We think of this as a path. So it's intuitively, basically you have your x, it doesn't matter what it is. You could have 2 points in your x. Let's call them x and y. And we're just saying that there should be a continuous function that, you can write from 0, 1 to x. It totally lives within your subset. Okay, it can't escape your subset at any point, and it just connects x to y. In this case, you could take a straight line path. Okay, if you can always take a straight line path, you say the set is convex. Okay, so there are interesting cases of convexity, connectedness, they're different concepts. Convex sets are always connected. And you can take the paths to be straight line segments, but they're always path connected. Okay, so now the question is, why is this deleted comb space, why is it not path connected? So you kind of intuitively understand that in an attempt to connect 0, 1 to any other point, you're going to have to jump somewhere. And that jump is going to result in a discontinuity of any potential f. But how do we rigorously prove this? I'm going to show you the proof right now, and it's a bit of topology, but a bit of very fun, intuitive idea, okay? So the point is going to be the following. So let's do this. I'm going to erase this definition, and then I'm going to talk about why this is not path connected. We're going to actually show that, say, 0, 1 can't be connected to 0, 0, okay, inside the comb space, okay? So let's do that. All right, so again, we're going to go a proof by contradiction. So let's say proof by contradiction is let f be a continuous function. Okay, so let f from 0, 1 to our comb space C be continuous, and such that, so let this be continuous, so this is our continuous path, such that f of 0 is equal to 0, 0, so such that f of 0 is equal to 0, 0, and f of 1 is going to equal to 0, 1. Okay, so it's going to connect our origin to our point 0, 1. How on earth it's going to do that? It's not possible, and we're going to have to prove that. So how do we go about doing this? I'm going to just write out our f of t. So f of t, you can think of t as time. I'm going to write it as f1 of t, comma f2 of t. Okay, so 2 coordinates of t. Okay, we're going to write it this way. Now, here's the point. Here's what I'm going to do. I'm going to use the fact that the interval is connected. Okay, that 0, 1 cannot be split up into 2 disjoint non-empty open sets, just like the definition I had earlier. That's something that actually has to be rigorously proved, even though again it seems intuitively obvious. But using that, I'm going to show that such an f can't exist. So what we're going to do is we're going to look at the set f inverse of 0, 1. We're going to look at f inverse of 0, 1. Okay, that means all the t, so that f of t is equal to 0, 1. So whenever our path touches our 0, 1, all the times it does so, that will be a subset of the closed interval 0, 1. And I'm going to show that this subset and the complement inside 0, 1, 0, 1 minus f inverse of 0, 1, this is going to be, both are going to be disjoint non-empty open subsets of 0, 1. Okay, I'm going to explain this as follows. The first point is that it's easier to see its complement is open. Basically, the complement, if something's in the complement, if a t is in the complement, that means f of t is not going to be equal to 0, 1. And if f of t is not 0, 1, f of t is some point in the space, you can always, it doesn't matter what it is, you can always find some small wiggle room around that point that's going to avoid 0, 1. And so because of continuity, there's going to be a small wiggle room around your point. So let's say our point is t. There's going to be a delta. Okay, there's an epsilon delta argument. There's going to be a delta greater than 0. So that t minus delta comma t plus delta, f of that is going to not touch. Okay, it's not going to touch 0, 1. So 0, 1 is not going to be in f of that for some delta greater than 0. That's just by continuity. Okay, because if f of t is something outside of 0, 1, f is continuous, you can just find a delta so that this is true and it's not touching 0, 1 within t minus delta to t plus delta. That's intuitive and also rigorous. Okay, now the next thing we have to do is show that this is open. F inverse of 0, 1 is open, and that's a little less clear. So why is f inverse of 0, 1 open? So if f of t is equal to 0, 1, why is it true there is a neighborhood of t? There is a delta so that t minus delta comma t plus delta is still mapped to 0, 1. And here's how we're going to do it. So I'm going to write it as follows. We're going to erase this from the top of the board. All right, so let t be. So now let's let t be inside f inverse of the point 0, 1. Okay, so this is the point 0, 1, which is this point here. Let t be in that. Okay, in other words, f of t is equal to 0, 1. Okay, it's going to be this point in the comb space. Now here's the thing. Because f is continuous, right? Because f is continuous, we can find a delta prime. So we can find delta prime greater than 0 such that the following is true. F of t minus delta prime comma t plus delta prime, and here this is an open interval, t minus delta prime comma t plus delta prime, is not going to touch the x-axis. Okay, it's not going to touch the x-axis. So in other words, the y-coordinate of f, which remember we wrote as f1 of t comma f2 of t, the y-coordinate is going to be greater than 0, always. Okay, so this is going to be true. We can find such a delta prime with this property because f is continuous. So if its value at t is 0, 1, you can find a sufficiently small neighborhood of t so that its value still remains above the x-axis by continuity. Now here's the interesting thing. Because of that, okay, if you look at f2 of this, if you look at f1 of this, okay, so f2 is this. So think about what the first coordinate of f has to be. Okay, we know that at some point, we know that f1, the first coordinate at t, is just going to equal to 0, right? Because f of t is equal to 0, 1, so the first coordinate of f of t is 0. And in general, we know the first coordinate has to be a discrete number, 1 half, 1/3, 1/4, etc., 1 over n, etc. It cannot be anything else because inside this range, we know that f is always above the x-axis. And above the x-axis, the comb space doesn't have many x-coordinates. All its x-coordinates correspond to peaks, which are of the form 1 over n. So we know that inside this interval, we can conclude, I'm going to just erase this here, we know that f1 of t is 0, and we know that f1 of t minus delta prime comma t plus delta prime, we know that that has to be contained in the set 1 over n, where n is greater than or equal to 1 is a positive integer, union 0, right? We know that. But here's the interesting thing. If the first coordinate is living in this set, and we know the first coordinate at t is equal to 0, that means that by the intermediate value theorem, f1 of this entire thing has to actually equal to 0. So therefore, f1 of this entire thing, t minus delta prime comma t plus delta prime, has to equal to 0. Why is that? Because if there was another point in f1 is a continuous function, because f is a continuous function, the intermediate value theorem would say that f1 would assume every value between 0 and that 1 over n. And that would be a contradiction because, as I said, there are no x-coordinates on the comb space above the y-axis other than the 1 over n's. So therefore, we know this is true. f1 of this has to equal to 0 by the intermediate value theorem. And of course, because f is entirely above the x-axis on this interval t minus delta prime t plus delta prime, that therefore means that f has to always be 0, 1 in that interval. Because that's the only point that has an x-coordinate of 0 and is above the y-axis. So therefore, we conclude that our set f inverse of 0, 1 is open. We've explained why its complement is open. So that implies that's contradiction. That implies the closed interval 0, 1 is disconnected because we split into these two islands, this disjoint non-empty open sets. Now you're going to love so much more topology. There's this video, check it out. It's going to pop up on the screen here. It proves that the closed interval is compact. 0, 1 is compact. It introduces what compactness is, reinforces concepts in this video, all from scratch. So it's more topology for you. Compactness is another fundamental concept. Please don't forget to leave a like and subscribe. I hope you love this video. I'm doing math at all levels on my channel, and I'm super looking forward to seeing you in the next video.